The following is my presentation at the joint MMM-INTERMAG 2022 conference, which I will give on December 29, 2021. In the presentation, I will talk about the features of parametric mechanism magnetization reversal, and specifically I will concentrate on mechanism 2, spin accumulation induced modulation of anisotropy field. Hello, my name is Vadim Zayats, and today I will talk about experimental evaluation of two parametric mechanisms of magnetization reversal in iron cobalt boron nanomagnet. The parametric mechanism can be used as effective low-energy recording mechanism for MRAM. The parametric magnetization reversal occurs when magnetization direction of nanomagnet is modulated with resonance with the magnetization precession. As a result, even a small modulation reverses the magnetization direction, as is in example shown here. Without the resonance, a weak magnetic field only slightly tilts the magnetization from its equilibrium direction without any chance of magnetization reversal. However, in case when the external field is modulated, so its phase and frequency are matched to the magnetization oscillation, even a tiny magnetic field reverses the magnetization. The effect is similar to a paramagnetic resonance for swings, when one small push does not do much. However, when several small pushes are done in the right time, the swing can turn around. As for MRAM, the threshold current for parametric recording can be as much as 10 times smaller than that for the direct recording. Main benefit of parametric mechanism for magnetization reversal is a small required recording energy. For operation of MRAM, there should be a substantial energy barrier between spin down and spin up states, otherwise the magnetization can be reversed by a thermal fluctuation. In case of conventional 2 and 3 terminal MRAM, the magnetization reversal based on continuous spin injection. During the whole time of magnetization precession and reversal, the spin injection should provide the energy larger than the barrier. In contrast, for parametric reversal, the required energy is much smaller. Due to its resonance nature, the energy barrier is climbed up by the tiny steps. As a result, the total recording energy could be an order of magnitude smaller than in case of the direct recording. As for example of swings, it is possible to turn around the swings by one hard strong push. However, it requires strong force and substantial amount of energy is wasted in the process. In contrast, the spinning energy is much smaller when the same swing reversal is achieved by several small pushes made at the optimal moments. The second merit of parametric magnetization reversal is the positive feedback loop, which is very unique for a magnetic system. Two conditions are required for existence of such a loop. The first condition is magnetoresistance. The second condition is modulation of magnetization direction by current. The positive feedback loop means that the precession of magnetization modulates the current due to magnetoresistance, and the same modulated current induces even larger magnetization precession due to parametric resonance. It means any existing magnetization precession, if meets the condition of parametric resonance, enhances itself until the magnetization reversal. Furthermore, due to the positive feedback loop, an effective magnetization reversal by a DC current is possible. when a parametric resonance is excited without modulation of any external parameter. It happens when a tiny thermally activated magnetization precession enhances itself until the magnetization reversal. The key property which is required for the parametric magnetization reversal is modulation of the magnetization direction by a current. Accordingly, four mechanisms of parametric magnetization reversal can be distinguished. The first mechanism is a reversal by magnetic field induced by spin accumulation. The magnetic field is along the spins and it tilts the magnetization from its easy axis. The amount of spin accumulation is proportional to the current. As a result, the magnetization tilting angle is proportional to the current as well. The second mechanism is the modulation of anisotropy field, which is also induced by spin accumulation, but in this case the spin are along easy axis. When there is an external magnetic field, the modulation of anisotropy field causes the modulation of magnetization angle. The third mechanism is the modulation of spin injection. The magnetization can be reversed directly by injection of substantial amount of spin polarized electrons. However, when the spin are injected at the optimum moment, the required amount of spin injection electrons can be substantially reduced. Of course, the amount of spin injection is proportional to the electrical current. The fourth mechanism is a reversal by earsted magnetic field induced by a current flowing in the MTG connection wire. Today I will talk only about these two mechanisms, focusing on the second mechanism. For the second mechanism, there are two cousin parametric mechanisms. The anisotropy field can be modulated either by current or by gate voltage. These graphs show experimental measurement of change of anisotropy field as a function of external magnetic field. Here the lines of different color correspond to a different current, and here different lines correspond to a different gate voltage. You can see that dependencies are very similar. It means that all features of this mechanism for current-induced magnetization reversal are nearly the same as that for the gate voltage-induced magnetization reversal. This slide explains the importance of bias in plane magnetic field for this mechanism. In absence of external field, the modulation of anisotropy field does not affect the magnetization direction at all. In contrast, an in-plane field tilts the magnetization, and the tilted angle depends on anisotropy field and therefore changes when the anisotropy field is modulated. These slides compare the magnitude of two mechanisms. The magnetization always aligned along the total magnetic field, which is the sum of internal magnetic field, spin accumulation induced magnetic field, and external magnetic field. This is experimental measurement of spin accumulation induced magnetic field in iron cobalt nanomagnet. The in-plane direction of this field substantially depends on the external perpendicular to plane magnetic field. At current density of 10 mA per square micrometers, which is about the critical current density for magnetization reversal in the best present MRAM, the value of the magnetic field is about 7 Gauss. This graph showed measured change of anisotropy field at the same current, which is about 17 Gauss. The calculated change of magnetization angle is the same for both mechanisms, meaning that effectiveness of both mechanisms is about the same in iron cobalt nanomagnet. For both mechanisms, the tilting angle is very small, but is sufficient for magnetization reversal parametrically. This slide shows how the magnetization precession enhanced parametrically by spin accumulation induced magnetic field. As you can see, there is a magnetization pulsation around axis whose angle constantly increases and sweeps between the left and the right. Each period, the pulsation angle increases per angle for phi. This slide shows the details of positive feedback loop for tunnel magnetic junction in which the magnetization of pin layer is in plane and the magnetization of free layer is perpendicular to the plane. Magnetization oscillation creates resistance oscillations, which creates current oscillations. The current modulates the spin accumulation and therefore the spin accumulation induced magnetic field. Since the frequency and phase of this magnetic field is exactly the same as that of magnetization precession, the magnetization precession is enhanced and the magnetization precession angle becomes larger and larger until magnetization reversal. In conclusion, I would like to explain how to distinguish between the direct mechanism of magnetization reversal, when a large amount of spin-polarized electrons are injected into the nanomagnet, and the effective parametric mechanism. I'm absolutely sure that in present effective MRAM, there is at least some contribution of the parametric mechanism for the data recording. Firstly, the direct recording is independent of the magnetic resistance, but the parametric mechanism is linearly proportional to the magnetic resistance. Secondly, the direct recording requires a spin injection deep inside nanomagnet. The spin accumulation at the interface is sufficient for parametric mechanism. Threshold current and recording pulse duration are distinguishably different between two mechanisms. Thank you.